Okay, thank you for inviting me, Hisham. This has been quite fun. This is my first time in this part of the world. So I'm told that I have to be super fast so that we don't get stuck in the desert later. Okay, so I'll tell you some recent work that I've done with these guys here, Fabio, Federico, and Sakura, in a paper that came out in August, but it's part of a longer program, so I'll try to give you a snippet of some of the things that we do. So the basic sort of world of where I will be talking about things is in terms of understanding global symmetries, right? So global symmetry in QFT allow us, in some sense, provide the basic skeleton, the framework by which this whole enterprise lies. And one of the sort of exciting recent developments is that global symmetry are more naturally thought of as somehow topological sectors of quantum field theory. And this sort of perspective has been rather powerful and seems to point to all sorts of interesting generalizations of what we should call symmetry. Some of them here are higher form symmetries, higher groups, non-invertible symmetries, categorical symmetries. Various aspects of these things actually showed up in this meeting already. Certainly in the framework of supergravity, we're familiar with higher form gauge symmetries and so on. So why in quantum field theory should we think of global symmetries having to do with something topological? This we can go all the way back to just thinking in basic quantum mechanics. What do we call a symmetry operator? A symmetry operator is anything that commutes with the Hamiltonian. From this point of view, you could see that what this means, any sort of local deformations that you do not change any expectation values you might get for the symmetry operator. So that is intuitively very topological. This sort of statement here is also invariant under the RG flow. The Hamiltonian can get renormalized, but the statement that the symmetry operator commutes to the Hamiltonian is preserved under RG flow. So in the Euclidean space, these operators are, in a very sharp sense, topological, and we will see this play out as we go. And even more interestingly, some of the aspects of symmetry that we know, which is anomalies, which are important, and anomalies, intuitively, you should think of them as something that measures degrees of freedom for your quantum system. Anomalies are preserved in the RG flow and under time evolution, and they help us characterize long-range phases of quantum systems, and we're used to doing this a lot. In this sense, also, anomalies are, in some sense, topological and constant in quantum field theory. So to make things a bit sharp, as an example, let's consider the Noetherian picture of symmetry. You have some current, which is conserved. So from this conserved current, you can define charges which act on your Hilbert space of states. And from these charges, of course, you can exponentiate to get appropriate operators, which we usually call symmetry operators. So these symmetry operators are actually topological in the following way. If you, there are two statements. First, they depend on some, in this case, where I have a current, a one-form current, the charges that I define in this way take domain over space of three manifolds, right? So they take in three manifolds, and their dependence on these three manifolds is completely topological, in a sense that if I take one charge on sigma and another on sigma prime, and I look at the difference is going to be zero due to the conservation law, always. And it's just, so that means that I can wiggle this surface as I wish, and it will not change the operator. So the charge itself, we should think of as topological operators that takes value on some on some lower manifold or some closed surface inside my spacetime. So you might ask, how does charge gets measured? And of course, this sort of relation here changes if I have charges, because if I have charges inside this volume region here, this thing here will pick up some delta function, and then I will get the value of the charge. What this means is that to measure a charge, you take your topological surface sigma and you collapse it, and then when it crosses any local operators or any operators that carry charge, then you would pick up a phase, which is what we would call measuring charge, or in more technical term, this is what would be the equivalence of obtaining the representation of the operator from which I'm interested in. So when U acts on O, it just gives you the representation of the operator O. So this picture, of course, is easily generalizable. This leads to the notion of the higher form symmetries, which we're very much familiar in supergravity when we have higher form gauge fields. And the simple picture you should keep in mind is that you can have topological operators of this kind defined on any higher codimension surface, and this higher codimension surface can link with some extended operators of various kinds. The dimensions have to add up to d minus 1, but you can define higher, you can define operators that take value on these high codimension surfaces, and they measure charges associated to various extended objects in various dimensions. Okay, so this is how we think of higher form symmetries. And the picture that I've described so far, at least from this point of view, no longer requires the Noetherian picture. So the operator that I have here includes both discrete and may also include various generalizations that you might care about, which we will come to. And in particular, what we're used to learning, at least in physics early on, is that if I take two symmetry operators, I multiply them, they have some group-like fusion, right? I label each operator by some group element, and then when I multiply them, I get another operator where the label take value in some symmetry group. However, in what I've described above, there is nothing that seems to that requires this statement exactly. In fact, what we might expect in general is that symmetry operators could follow some more algebraic structure, right, with some structure constants that appear here. So this is interesting because this tells us we shouldn't think of symmetry as forming a group, but this more algebraic structure. So this sort of opens the door for all sorts of other additional things that we should think about, not just generalizing as higher forms, but we can also generalize in a truly categorical way, which I will not have much to say, but this is the goal. In particular here, what this means, if I have this algebraic structure, I have to allow for the possibility where you have something that looks fairly non-unitary, but it makes sense in other way. You can ask me questions about that. That if you can have operators where if you multiply them with their conjugate, their charge conjugate, and so on, instead of getting one, you get something else. Okay, so this opens for the possibility of having symmetry operators that are non-invertible. Right? So you cannot undo them when you insert them in your path integral, for example. Okay? And this is going to be the subject of the talk today, and how do you realize such a thing in a holographic setting, and why they're there in a holographic setting also. Of course, this has been known a lot in 2D CFTs, right? So we have Verlinde lines, which were known since the 80s, you have anyons, which had been known for a long time, and so on. You have, 2D Ising model at the self-dual point of Kramer-Wanier duality. You also have these things, and it has been known for a while. The sort of thing that is interesting is whether such a structure like this can exist in higher dimensions, right? Do four-dimensional quantum field theories that we care about, simple quantum systems, actually admit such a symmetries in such a symmetry structure? And if they do, what is their role and what is their physics? Okay. So recently, this is the thing that has changed, and it was sort of surprising in a series, first by these two papers, and then various generalizations, some that I'm involved with, some others are involved with, that sort of point out that where explicit examples in four-dimensional quantum field theories were constructed, not just exotic theories, but down-to-earth theories that we know and grew up with and care about. So the talk will actually try to follow those examples and see what we can do with them. So it's been rather surprising just within the last year and a half that we've discovered that these things can exist in run-of-the-mill quantum field theories. So the key question that I want to answer today, so if we can find examples of these things in quantum field theory, how do they appear in holography? Why is that a reasonable question to ask? Is because if we understand how such asymmetries would appear in holographic settings, then we can use the whole enterprise of string theory and so on to actually study and try to understand where they're coming from. And more interestingly, if you have something that is so non-unitary in this sort of a way, how do you talk about representations? How do you talk about the additional states that you need to add in so that you have a well-defined unitary quantum system? Okay? So the goal is to then understand how to do this in holography, because it will also allow you, with the power of string theory and other things, to try to better understand the full categorical structure that should exist for them. Okay? To do this, I will try to keep a very specific example, and then in a specific examples, demonstrate where this symmetry is in holography and how it comes from. Okay? So any questions so far? So let's consider something that many of us learned early on, which is super Yang-Mills theory. We will take n equal to 1 super Yang-Mills theory. Why n equal to 1? Just because I can write holographic systems and solutions exist and are more immediately accessible when they're supersymmetric. So let's take the simplest supersymmetric theory that we all learned and studied at some point, which is n equal to 1 super Yang-Mills theory. So here I will demonstrate that these theories, for example, do admit these non-invertible symmetries, and then we will see how they appear in holography. So first thing to note is that if I just take SUM theory, it has a one-form symmetry, right? And what is this one-form symmetry? This is a symmetry that acts on Wilson lines. If I have SUN super Yang-Mills theory with global gauge group SUM, then that theory has Wilson lines as extended operators, and those carry charge under some discrete symmetry, which is a ZM discrete symmetry, and it's a one-form symmetry because extended operators, but because you have extended operators, not local point operators. So this super Yang-Mills theory, because it's supersymmetric, if you look at the classical theory, it has a U1R symmetry, which is easy to see, but this U1R symmetry is broken by the ABJ anomaly. Okay, there's an ABJ anomaly that breaks this continuous U1R symmetry. In order to restore such a symmetry, we know you have to add some matter into my system, but there's an ABJ anomaly that breaks this symmetry, but it doesn't completely break it. It breaks it down to a Z2M discrete zero-form symmetry. So n equal to 1 super Yang-Mills theory also have a zero-form symmetry which acts on local operators, which is discrete, which is Z2M. Okay? Now, this sort of a discrete symmetry talks to the one-form symmetry, and it talks to the one-form symmetry in a sense that there is a mixed anomaly between these two. This mixed anomaly is inherited from the ABJ anomaly. Okay? The ABJ anomaly has some residual effect where it breaks the continuous symmetry, but it generates a mixed anomaly between the discrete one-form, zero-form symmetry with a discrete one-form symmetry of n equal to 1 super Yang-Mills theory. So we can write this anomaly in this way, where we think of A1 is a background field associated to the zero-form symmetry, and it takes value in H1 Z2M. And we have the Pontryagin eigendual of B2, where B2 here is a background field associated to the one-form symmetry. Okay, so there is a one-form symmetry, and there is a background field, which is a two-form, which is a discrete two-form, which takes value in H2 of the space-time with coefficients in Zm. Okay. Go ahead. You can model it as a locally constant one form. Yeah, that's right. But really, it's an element in this cohomology group. So hence the cup product. So morally, this is why I say this. So morally, this is saying A wedge B2 squared. But this is, of course, ill-defined for various pictures because it's, here it's continuous terms. This is not a gauge invariant object. What do I mean by this? But this thing makes sense mathematically, but in standard physics language, you say this. And in fact, this is so already, the fact that there is this guy versus this guy already should give you some worry, because I want to understand these things in supergravity, but in supergravity we use continuous fields, right? And that's going to be an important issue that has to be resolved along the way. How does supergravity see these things when only supergravity knows about continuous fields? Okay? Yes. So their symmetries is the definition here of symmetry is enhanced by any operators that is preserved under any Hamiltonian evolution, right? So the definition that you provide is certainly true in that case. So a symmetry operator, you should think of anything that is preserved under an RG flow that commutes with a Hamiltonian, that gives you some constant in your system. You should consider that as a symmetry operator. Okay, so what you're trying to get at is more closely related. How do I think about representations of these things, right? And that's an interesting question for which many people are thinking about and trying to understand how to do representations and how to compute characters you might associate with these things. But the point is that when I give you such a collection of operators, they satisfy some algebra. And what you really want to ultimately understand is the representation of such algebra, right? And this is an algebra that takes value over surfaces in your space-time in a way that is topological. Did this answer your question better? Partially. Okay, good. At first pass, when we introduce these things, they seem relatively straightforward and obvious, but then when you try to reconcile it with many things that, we sort of instinctively think about as symmetries, there is some corrections and some things to explain. So that's good. Okay, so coming back to this thing, so I have this zero. I did not wish to do that. I have this this zero form symmetry. Right, is generated by some operators, as we described earlier. There must be some extended operator that takes value on some three-dimensional surfaces that sort of wrap local operators and measure charges. So we will label that as D3-1M. So you can literally think of this as being some surface that I would insert in my spacetime, and they would measure some local operator where this is M3. And then I can collapse M3 to measure the operator. So I can take two of such operators, D1 and another one, D1, and I can stack them on top of each other in M3, so that would be some fusion over the two. And when I fuse them, I should get a third operator. But since this is a group, I'm describing here a discrete symmetry group, so the product, this group is such that when I take 2M of these on top of each other, they just act like an identity operator, which is just a transparent surface. Okay, so this defines the Z2M discrete symmetry. Now, something funny happens because you have this anomaly. I can take my quantum field theory and I have one-form and a two-form symmetry. And one thing that we're used to doing is turning on background gauge fields for symmetries. And we do this to measure anomalies. We do this to measure various properties of quantum field theory. So you can ask, given this operator, what happens when I turn on background fields for the one-form and the zero-form symmetry? And if I turn on to the background field, which is A1 and B2, in particular when I turn on B2, because there is a mixed anomaly, what this means is that this operator, D3, will transform non-trivially in presence of the background fields, right? So if I have this, so what this simply means that I have the presence of the anomaly, intuitively, the way you can think about it is somehow this D3M is not left invariant by a gauge transformation involving the one-form symmetry. So this one-form symmetry is given by B2. So if I turn on B2 and I do a gauge transformation with B2, then this D3 will transform, and that is not something that you would immediately want. But that's okay at this level, simply because this is a background field. And in fact, you can easily fix it. When you turn on a background field, you can easily fix your operator to make it topological again, simply by multiplying to it by this number, right? So this is a pure number, right? Because B2 is a background field, where I take the Pontryagin square of B2, and then I just multiply it here. So then when I do a gauge transformation in presence of the background field, this is going to be left invariant, and it's topological again. So here, when I do this, I insert, so B2 is integrated in M4, and M4 is anchored on M3, where I define this operator. So everything so far is good. Nothing dramatic happens. So the case where you will get into trouble is the following sense. So any questions about that process? Okay. So, however, when I try to gauge a symmetry, usually when that happens is that when I gauge a symmetry which is anomalous, which has a mixed anomaly with a different symmetry, I usually break that symmetry, okay? So this thing, what this means here is, so what this means in this case here is exactly in this procedure where I turn this thing on, this thing on to define this new operator, although this looks like it's a fix, but because B2 would be a gauge field, right? This is not a well-defined operator. I shouldn't have naked gauge field floating around when I define these things, so this is not a well-defined operator. So when does this happen? This happens in the following way. So I take my one-form symmetry, which, remember, it was a center symmetry, which was acting on Wilson line, and now I'm going to gauge that one-form symmetry. So for super Yang-Mills theory, if I gauge this one-form symmetry, I sum over. The Wilson lines are no longer operators in the theory, but then you get a 't Hooft line. So you have a dual one-form symmetry, but that's not going to play a role here. The key thing here is that when I gauge this one-form symmetry, this is equivalent to changing the global form of the gauge group. The gauge group, instead of being SUM, now is SUM mod ZM. I've gauged the center symmetry, so I've divided the gauge group with it. And in this case, these operators which generated the zero-form symmetry are no longer gauge invariant, okay, as I described earlier. And naturally, we would say the Z2M symmetry gets broken down to a Z2 symmetry. This Z2 symmetry is a Z2 symmetry which just measures fermion number in this supersymmetric theory. It's a boring Z2 symmetry. However, there is a fix you can do to try to restore this topological operator. And the fix that you can do is something that we've done many times before, is since this operator is defined on a three-dimensional space, one thing you can do is consider it's defined on a three-dimensional space and it must be topological. I'm certainly allowed to turn on a non-trivial topological theory on such a three-dimensional space, right? The constraint is I just want topological operators that can generate such a symmetry. So, but since I have this 3D M3, I can turn on some TQFT that lives on there. But it cannot be any TQFT. The TQFT that I turn on have to be designed in a way to actually allow me to restore the invariance of the full operator, right? So this is the process of stacking. And if I want to think about, so what do I need to do to make this invariant? I need to turn on something on M3 such that it can cancel the mixed anomaly that I observed earlier. So if I can cancel this mixed anomaly, then I can construct an invariant operator. So now I want to think about 3D TQFT. The simplest 3D TQFT that you could imagine that could help is to consider U1 level M-Chern-Simon theory. So U1 level M-Chern-Simon theory itself also has a one-form symmetry. Right? It has a one-form symmetry, which is acting on the actual anyons of this theory. So what I can do, and that one-form symmetry has an anomaly, which is constructed from some four-dimensional space, which exactly is given by this expression. So what you can do is you take the U1 level M-Chern-Simons, and you stack it on M3, where you define the D3 operator, and then you gauge a diagonal subgroup of this one-form symmetry. Instead of gauging the full one-form symmetry, instead of gauging, you gauge the diagonal one-form symmetry on the operator, and in the bulk of the Super-Yang-Mills theory, the one-form symmetry is also gauged. Right? And this is the thing that I wanted to do. But if I gauge the diagonal symmetry on M3, because it has the same mixed anomaly, it will cancel the anomaly contribution that was coming in from the bulk. There is a sort of inflow procedure that's happening that's allowing me to turn on degrees of freedom on the topological operator, then I can use this to cancel the mixed anomaly that was making the operator ill-defined. So this is usually what's referred to as stacking. So I take my original operator and I stack to it a U1 level M-Chern-Simon theory in this way. And this object now is well-defined as an operator in the 4D theory. It's well-defined and it's gauge invariant, okay? However, something interesting happens now. If I take its conjugate, right? So far what I've done is all allowed in the rules of quantum field theory. If I take now the conjugate of this operator, N3, and I fuse it with N3 original, so when I do this fusion, naturally you might expect you should get the identity operator, but you don't get the identity operator. When you compute this thing here, the original part, which was the D3, of course, it was invertible. It was in elements of Z2M. It was invertible, so that becomes 1. However, if I look at the contribution coming from the U1 level M-Chern-Simon theory, which has to be coupled to the bulk fields, it gives me something that is non-trivial, okay? It gives me something that we refer to as a condensate defect. So what it does is, so D2M are going to be some new topological operator that gets generated, and the way you should think of this is that I have my original three-dimensional surface where my operator is defined, and on this 3D surface, I can turn on additional modes that take value on the H2 along this, right? So this is, you should think of this as a mesh, right? There's a mesh, and on this mesh, I am turning on additional operators. There's these operators here, D2M, that are being turned on, that are summed with some coefficient sitting here. There's some normalization, but that's not super important. So this is the thing we refer to as a condensation defect on M3. Go ahead. Yeah. Yes. Mm-hmm. That's right. So that theory. So the way that I have to make sure that I am doing the discrete symmetry. So actually, so Chern-Simons theory is something we can write down easily. So the action, so what it means is that I have D3, which I had, and to sort of, so let me rewrite it for you so I can be more explicit. So I have to have a path integral over new gauge field A. I have my D3 operators M, which could also depend on the background field B2 of the bulk gauge field. Then the Chern-Simons part that I'm adding, I have an integral. I would have an M over 2 ADA, right? This is the standard Chern-Simons. But I have to couple it to the bulk field, right? And the coupling of the bulk field is what identifies the one-form symmetry of the Chern-Simons with the one-form symmetry of the bulk gauge theory. So I add this to A wedge dA, A wedge B2, where B2 is the bulk gauge field. So you see, this is a quantum operator, right? Because I'm doing a path integral over A. But you see, this thing lives completely on M3, right? So this thing is not in the bulk. It lives completely on M3. And this is a coupling here that's allowing me to to basically mix the Z2 of the bulk to the Z2 on the surface. So now, so this thing here looks rather benign, but if I take two of them and I multiply and I do the path integral, I don't get 0. I will get a bunch of residues. So precisely because of this term here that you see here, right? If I take two of them and I stack, there's an I, which will flip the sign, and I stack the two of them and I evaluate the path integral over the Chern-Simons fields, I would get a residue which will depend on the gauge field here. So this D2 is coming from the part when I integrate out the A's from there. Come again? No, there are gauge fields on the defect. Oh, no, not quite. So there is a dressing. So A is a topological theory on the defect, and it is dynamical on the defect. But the point is, when I take two of the defects and I fuse them, I get a third defect. That third defect does not look like the same as the original one. Okay. No, it's a quantum field theory. I'm defining quantum field theory for you. I'm defining a TQFT on M theory. That's a path integral. This is equal to N. So this is N. Right? Yes. That's my refined operator, yes. I mean, that is in the same sense that you would say that if I look at the path integral of gauge theories, that the gauge field is non-dynamical. Very good. So the question is that if I look at I'm perfectly allowed to take the operator N and ask topological expectation values on N. Those would be non-trivial, right? On N. But from the point of view of the bulk, it's a trick. Right? From the point of view of the bulk is a trick, but on M3 itself, there is non-trivial dynamics. Right? But it's still a topological theory. Sorry. But it's still a dynamical, but still, from the point of view of the bulk, I just have a topological operator. It doesn't care. But this is, indeed, if I'm looking on the surface, this is non-trivial. This is quite important in the brane realization of these things, which I will unfortunately not get to, but we have a long hour drive that I can tell you about. Okay? But the point is that when I now take this N operator and I fuse it with N dagger, so this, I have to integrate over both. I can evaluate those path integrals completely. In fact, I will do something like it later. Then you get a mesh on M3, where this mesh is what you call a condensate defect. So what this mesh means is that I've turned on a bunch of lines which live on H2. And what are these lines? You think of these lines are exactly coming from the holonomies of B2 on M3, right? So that's a condensate defect, and it turns out that defect is also well defined and is also topological. Okay, good. Okay, so I told you the playground which I want to use, and I've pointed out why this theory has non-invertible symmetries. So now I'm going to tell you how to realize them in holography. And the context that I will use is Klebanov-Strauss law and Klebanov-Tselan, which is take type 2B on ADS5 times T11. So this is a famous, this is a theory on the conifold, which is mass deformed. But ADS5 times T11 is dual to the quiver, to this type of a quiver where M is set to 0. But I'm going to turn on some F3 flux, right? So I have an F3 flux turned on, so the geometry is supported by N units of F5 flux, and then I turn on M units of F3 flux, so which is wrapping some 3 cycle inside T11. So this setup here in string theory is going to be dual to this gauge theory, which is this quiver gauge theory, where each one of these guys corresponds to an SU, to a super Yang-Mills theory, and then these lines, there are hypermultiplets that are charged in some bifundamental representation. So this theory has very interesting dynamic to it. It has what's called a duality cascade, meaning that when M divides N, I don't want to do that. When M divides N, in fact, it has this cascade in general where it experiences different phases, confinement, deconfined phase. But in one particular setup is when M divides N, it flows to a single node of SU M super Yang-Mills theory, plus some additional things, which is due to the fact that you have some global SU2 global symmetry, which is not super relevant for this talk. But the point is that this will flow to an SU-M super Yang-Mills theory. So this setup here of type 2B on ADS5 times with F3 flux should be considered dual to this SU-M super Yang-Mills theory. Okay. So what this means then, this is a setup in holography where I should be able to realize these non-invertible symmetries. So there are 2 questions you could ask here. There are 2 questions here. One is, we certainly are used to thinking about ADS-CFT and holography as being a proper stringy thing. Then if I want to understand these operators, then I could ask what are the stringy objects that are dual to these topological operators. That's one question. And the answer to that are going to be branes that wrap interesting cycles, and these sort of interesting Chern-Simon theory that I'm forced to turn on are going to be related to the fact that branes have Western-Mino terms. And those Western-Mino terms will induce these interesting theories which will make it non-invertible. So I will not have time to talk about that story in detail, so I'll just give you that answer. And then there is another question you can ask, which is that another way we think of holography is we take the string theory and we reduce it on the internal space where we just have an effective theory defined in ADS5. And then from the picture of having an effective theory in ADS5, I should also be able to see these symmetry operators, these topological operators emerge. Okay, so this is the story that I will tell you now. How do those symmetry operators emerge from this bottom-up effective picture of holography? So the first thing to tell you is what is the effective theory in ADS5 and how the symmetry emerge. So I will just table it here for you. I have various low energy excitations to consider. First, I have T11, which has a U1 isometry, which is what usually is the R symmetry. So I can turn on that guy, so that will have some gauge field in the bulk, which is A1. Then I can take my 3-form flux, wrap it on the 2 cycle of T11. That gives me some field, and H3 has an external component which gives me a B2 field. And then I can take F3 also in the external ADS5, which gives me a C2 fluctuations. And finally, there is one more field which is interesting, where I can take the 5-form flux and wrap it on the 3 cycle of T11. That will give me some gauge U1 gauge field beta 1. So all of these fields are constrained by Bianchi identities here, right? And the fact that you have m units of flux is going to play out for F3 in a rather nice way. So you have these Bianchi identities that show up here, and before I express the effective theory, I need to solve those Bianchi identities, and this allows me to introduce local fluctuations. And the solution you can write down is in this way, and let me explain various parts because they're going to be important. First, if I look at just the F1, it's going to be related to C0 through the Bianchi identity. And because I have these m units of flux coming from F3, there is going to be some additional piece that appear here, which is coming from this Bianchi identity term, okay? So if you observe this thing here, what is happening here? What is happening here is that this is a Stuckelberg coupling of A1 with C0, okay? And what this tells you is that the U1 gauge theory associated to A1 is going to be spontaneously broken in the bulk, right? It's spontaneously broken because there's a Stuckelberg field coupled to it. That's one statement. And then if you look at B1 and also B2, they are mixed due to this Bianchi identity. So I have a G2 here, which combines beta 1 with B2. So B2 was going to be a U1 one-form symmetry in the bulk gauge theory, okay? But now that is also being Stuckelberg coupled to beta 1. So that also means that that U1 gauge symmetry in the bulk is also spontaneously broken, okay? So where are they broken? It's easy to see what happens to them. So the U1 R symmetry here is going to be broken to a Z2M zero-form symmetry owed to this fact here. So actually I have these things written here. Okay, so the A1 gauge field, which was the R symmetry, becomes spontaneously broken to a Z2M zero-form symmetry. And the B2 gauge field becomes spontaneously broken to a one-form symmetry, which is a Z1M thing. And all of this just follows from reading from the constraints imposed by the Bianchi identity in trying to compute the effective theory, the effective low energy theory. There is additional data here that I've kept. In solving the Bianchi identity, we impose that both C0, A1, beta 1, B2 are globally well-defined fields. So that means that the cohomological data associated to these fluxes are going to be independent information that I have to keep track of. So F1b and G2b are exactly those cohomological data that I will keep track of. And keeping track of them is going to be the key to allow me to describe these anomalies in supergravity, okay? So I have local fields, which when combined in this Stuckelberg way allows me to model these discrete symmetries. And the cohomological data that I will need to talk about the anomalies are going to be kept track of by these things here. And exactly as expected, F1b lives in H1 with coefficients in Z, G2 in H2 in coefficients, and similarly in F3. So now what I can do is compute the effective action associated to all of these fields. And what you get is this. So let's explain the different pieces. Okay, so first you have these terms here, which are BF terms, right? So you have these BF terms, and BF terms are well known as being the Lagrangian for discrete gauge symmetry. So we have this part. And then you have these higher couplings that appear here, okay? So this is a purely supergravity term, which completely makes sense in supergravity. And this G2B here has its origin from the B field, okay? It has its origin from the B field. So actually the way we think of this object, which is a well-defined object, is the integral lift of B2, right? So B2 is a discrete gauge field, so it takes value of a discrete element. So G2B is the integral lift of B2. So what supergravity sees, not that the fact that we have B2, which is valued in a cohomology with a discrete coefficients, but what it sees is the integral lift of the object into the integral, into the integer cohomology, okay? Yes, good. That's exactly the point, right? So the point is that when this is why I started by describing all of these from the string theory. From the string theory, all of the fluxes have quantization conditions, and those quantization conditions is exactly what's telling me these facts here. But still, string theory doesn't completely tell me doesn't completely give me the discrete data. Right? What it tells me is object and integral cohomology. Right? There is a further step which I see dynamically, and then you have to reinterpret these as lifting those terms. I mean, you can have obstructions to that lift, but I will not worry about that here. Okay. Good. So this is now the key point, right? So you might imagine that in supergravity you would get something that is like A1 wedge B2 B2. You can never get such a thing because it's not a gauge invariant object. You should not get such a terms because that's very bad. But if you keep track of the quantization conditions carefully and solve the Bianchi identities where you really split the pieces that are dynamical and the pieces that have to do with the cohomology, then you can actually recover these terms, these anomaly terms. So this guy is in the bulk is the thing that is dual to the anomaly that we were just talking about earlier in the field theory, because this is a mixed anomaly between the zero form symmetry and the one form symmetry. So the bulk supergravity can capture that in this very nice way. So now the question is, how do I go from writing this bulk gauge theory to actually then capturing the symmetry operator that I want? So let me try to, oh wow, time is done. Oy. Okay, I will take 5 more minutes. Sorry. Okay, so there are 2 stories to tell here. One is that first, there's a distinction between the SUM theory and the PSUM theory, and the supergravity should know about that. How does it know about that? It knows about that because when I take this action and I have the ADS boundary, I have to pick a boundary condition. And your choices of boundary condition is going to distinguish these different global gauge forms. So for example, if I fix the B2 then to some constant value, then this constant value becomes the background field for the ZM one-form symmetry, right? If I fix A1 to some background value, then that background value becomes the background gauge field for the Z2M discrete form. But then in doing so, I have to sum over all of the other gauge fields in evaluating the path integral of the bulk theory. Similarly, to get the PSUM, I also do the same thing, but here I have to fix the magnetic dual of the electric one-form symmetry that I want to gauge in the boundary. So I fix C2, but then I have to sum over B2, and I have to also sum over G2. So that is the equivalence of having that gauged in the boundary theory because it's not a global symmetry, it's summed over, okay? But then I also fix A1 so I can have the one-form symmetry. Then the object that I want to compute is this thing here, which when I push it to the boundary is the thing that measures the charge. And the trick that you use is that, so in the bulk, what you have is a gauge symmetry. In the boundary, you have a global symmetry. But if you have a gauge symmetry, there is a well-defined notion of symmetry generators that we know of. And the way you can obtain such a symmetry generator for gauge symmetry is good old Hamiltonian quantization. Okay? So you can consider now the gauge theory that I've defined earlier for you. And what I will do is I'll pick a time direction, and this time direction becomes a radial direction. And I can consider a Hamiltonian quantization of that theory. So the Hamiltonian quantization of that theory is going to have Gauss law constraints, right? Because I have a gauge theory. And those Gauss law constraints is what we call the symmetry generators, the gauge symmetry generators in standard gauge theory. So I'm rushing through this, but let me just show you how it works. More specifically, if I look at the effective Lagrangian in the bulk of some gauge theory, which I split in this way in Hamiltonian quantization, if you actually study this thing, you will find that it does not depend on the time derivative of A0. So the time derivative of A0 isn't there. So actually A0 is a Lagrange multiplier for your theory. This is just, A0 is just parameterizing the extra gauge mode, okay? So what that means is that the momentum conjugate of A0 isn't there. So you have to interpret this relation here, right? So classically, you get a classical relation which is of this kind from the Euler-Lagrange equation. But this here is an operator that depends on the field, and the quantization, you cannot just set it to 0. But what it does is that it generates gauge transformation, right? So you can define some operator in the gauge in the quantum theory, which looks like this, where this operator, when it acts on anything, it generates a gauge transformation where lambda p is the gauge field associated to A. Okay? So it turns out when I look at the Gauss law constraint, this thing is always going to be closed, and it defines what we usually call the phase charge here. And then you can integrate by parts, and you get this object that appears here, where lambda is the gauge parameter that we typically have. Now we're almost done, because this object, when I consider this object of this kind, I can think about doing some singular gauge transformation, where I consider gauge transformations that look like this, of this form. So what this means, this is like I do a gauge transformation where I have lambda is like a constant inside some M3, and then outside is 0, right? So that generates a gauge transformation in the bulk for me. And that gauge transformation, I can put it inside here, and what it does for me, it evaluates and defines an operator that lives on M3. Right? It will just yield an operator that just lives on this submanifold M3. So this thing now exactly looks like this, which we identify, and when I push it to the boundary, it's a topological operator. Okay, so this is the bulk derivation of this topological operator that I wanted to obtain. Okay, so the thing that it means is now, given that supergravity action, that effective action that I computed, what I need to extract is the phase charge. And if I get the phase charge, then I have the symmetry operator that I want to compute, and I have a holographic construction of it. Okay, so I'll just skip a few more things and then just show you what the answer is. So if I compute this, I can compute this operator explicitly. So let me just get to the answer, since so I can compute it explicitly for the one-form symmetry. And when I compute it explicitly for the one-form symmetry, what I get is something that at the end of the day that I could reconstruct, which looks like this. Okay, so you can go ahead, you take the action, you vary it, you compute the Gauss law, and then you can extract the operator from the Gauss law explicitly, and then in the bulk of the gauge theory, you get an action that looks like this. So there's a couple of pieces of data. This part C3 is actually the part that would be related to the D3, right? If I just take integral of C3 and push it to the boundary, this has been known since Witten in the 1998 that that is a topological operator that just generates the global symmetry in the boundary. But the effective action that I've constructed also turns on these additional modes and exactly turn on this Chern-Simons term that I wanted, where I have this G2B, which is exactly the background fields, which I was, which not the background field, but the gauge field that was present in giving me the mesh. So this becomes the operator for the PSUM theory, and indeed, in the bulk of the supergravity, you can check that this thing is non-invertible, and it does exactly the thing that you want to do. Okay, so this discussion here gives you a symmetry, a derivation of the symmetry operator, right? So in the field theory, if you remember, we had to sort of engineer the symmetry operator by figuring out how to be creative. We have to figure out something to stack it and so on. But in the supergravity, you actually do a derivation, right? You explicitly derive it by using the Gauss law constraint that, from this theory, which is in terms of continuous fields. Okay? So the one thing you can actually ask is, if I put this in the full string theory, what are the actual stringy object that gives you this? So this you can compute. It turns out it's going to be D branes. So what this implies that somehow this sort of algebraic structure that is algebraic symmetry structure that's being generated for field theories is somehow going to be dual to some fusion structure of branes. Right? If I have the branes that I could construct in the bulk and ask how do they behave, so for example, the way to realize the non-invertible structure of that I see in this field theory, so you can think about this, what it looks like in the bulk. In the bulk, this corresponds to, there is a brane that you associate to the symmetry operator, and you can take the anti-brane of that, and you can fuse them, collapse them on top of each other. What you get in that case is some tachyon condensate, but that tachyon condensate has some residue, and the residue of what it has is going to be some D3 branes, and those D3 branes will encode these condensate operators, for example. So you can push along this direction, and you can see these structures further. And for those who are curious, I can also tell you a bit more about that in a bit. So I'll stop here since we have to go to the safari.
Great, thank you. So I appreciate this. Ibu, in the expense of interest of time, I think let's ask the further questions along the way. How's that?
That is perfectly fine.
Okay, great. Let's thank you again. Thank you so much.